Hey guys, Mr. Roach here. It is Friday afternoon, November 14th. There were a number of people gone for the field trip, so I thought it'd be good to record myself teaching this lesson. Hope you guys have a great weekend coming up. Just know that this lesson is still part of our test coming up next week, is worth reviewing. So daily problem here, I don't think I'm going to spend too much time on it because we were doing pretty good on the quadratic formula. The one thing that I want to emphasize is always equal to 0. If we're using the quadratic formula, the reason is we're looking for our x-intercepts. So finding those would require us to get this side equal to 0. So I've got 9x squared minus 18x minus 1 equals 0. And then I can, be off to the races using the quadratic formula. And we are going to see this pop back up later on in this lesson. The lesson today is all about applications of quadratics. So looking at our goals, representing real world scenarios using what you know. Might be the quadratic formula, might be complete the square, might be factoring. I'll tell you mostly with this, it's going to be a lot of quadratic formula because we're going to have some decimals. With that in mind, on Schoology, we have a calculator for you right here that you can use if you need an emulator, and you will want a calculator on the test next week. If you want to know the trivia question, it is a name that artist who painted this. You can pause and make your guess. It's Vincent van Gogh. Vincent van Gogh. Cool. All right, so this unit, we have covered different ways to work with quadratic formulas. We've mostly been solving them for the x-intercepts, but we've got some other things along the way too, like the vertex and the axis of symmetry, and that would come from complete the square. Factored form is the probably most efficient, quickest way to find your x-intercepts there. And then over the last couple of days, we added in the quadratic formula as well. One thing to know is that I am going to be talking about applications of parabolas, which is projectile motions. It's things flying through the air. For instance, a football. And if I'm flying through the air, I've got some interesting things that happen, right? So as J.J. McCarthy throws this absolute dot to the back of the end zone, we dunk on some Packers, that sort of thing. Pretty natural for us Vikings fans. A couple of things that's kind of interesting. Number one, the y-axis is going to be height. How high did he throw that ball? How far off the ground was he when he actually threw it? How far off the ground was Justin Jefferson when he caught it? That sort of thing. You'll see this a lot of times as h for height. And my x-axis is actually going to be t for time. So how long was that ball in the air? Now, some interesting consequences. Number one, take a look at where his arm is. If I just pick an easy coordinate point that's kind of close to it, two things I can see. Number one, that this ball was 2 units, maybe meters off the ground when he threw it. But what about this t value? That guy's negative. You can't have negative time. So interesting, we'll talk about it. We call it extraneous when I can solve for it algebraically, but it doesn't really make sense in the context of the real world, in the context of my problem. So that's one interesting thing. Second interesting thing is we're not always interested in the x-intercepts, because if this ball was thrown with an x-intercept, that means it hit the ground, and hitting the ground would be an incomplete pass. It's not going to actually make that connection with Justin Jefferson. So if I don't have a graph, how can I algebraically find the time it takes to get to a certain height? Maybe he's going to catch it like 8 feet off the ground or whatever that y value happens to be. So we're going to see a problem. It'll be the last problem that we do. When I don't want to know when it hits the ground, when it's at a height of 0, I more so want to know, like, hey, when is this going to be 8 feet off the ground? Or they think the problem is 5 meters or 5 feet off the ground. So kind of interesting is I get some different twists and turns of parabolas and no negative time. And then I might not necessarily want the x-intercepts, but we'll show you how to deal with that. Projectile motion is a function. It is a parabola in standard form that looks like this. I've got negative 4.9 t squared. We call that V naught. It means when there's like not a thing happening, right? That's at least what I think of. V naught means what's your initial velocity? How fast was this thing launched? Was it thrown? Was it put into the air? And then out here is H naught, H of 0, was the initial height. So from what height was it thrown? Negative 4.9 is going to happen in pretty much all of our equations. That has to do with gravity. Kind of interesting is it's negative. So our parabolas are always going to be upside down, meaning we have a maximum vertex. And 4.9 has to do with the constant of gravity. Gravity pulls back to Earth at 9.8 meters per second squared. So you have that connection there, right, with 4.9 and 9.8. That would be double 4.9. So I've been looking at a couple of these examples just to give you some more concrete things. Here's an equation. And just by looking at this equation, I can see gravity. That is my gravity constant. 15 is the initial velocity. That's what this question is asking. Maybe it was 15 meters per second. Maybe it was miles per hour. I don't know, some sort of unit. 15 was the initial velocity. And then just kind of a bonus question. It would be from a height of 115 units tall. So feet, yards, miles. I don't know. Miles would be kind of crazy. Another one is what's the initial height of this equation? Initial height is here. Interesting and worth knowing that that would be a t value of 0 because no time has passed at all. So that's the initial height would be 98 units. And then we can kind of construct our own equations. So an object has an initial height of 7.6 meters, an initial velocity of 4 meters per second squared, 4 meters per second. Sorry, it's, Friday afternoon, just out here grinding through another math lesson at 4:10 p.m. I would set it up like this: my initial velocity next to t and my initial height out here. That's my c value, my y-intercept. This one will be relevant for your homework. So if you're watching, hey, good for you. You've got a free homework help. It starts on the ground, would have no height at all, right? It would be a height of 0. So I think there's one about golfing or something like that on the homework. Negative 4.9 t squared, an initial velocity of 70.5 meters per second. And then on the ground would be just plus 0, which I'm not even going to write. So there's my equation there. Cool. Hopefully you're feeling pretty good about this. Hopefully you're feeling pretty good about just kind of the setup. The biggest thing that I would recommend is, number one, can you draw a diagram? It's really, really helpful to draw a diagram of this. And number two, can you use that to figure out what am I looking for? What am I trying to find? What question am I really trying to answer? You kind of have to break down the words and interpret what the problem is trying to get you to look for. So here's my equation. I've got my initial velocity, initial height. I've got gravity chilling out front. So that equation represents an object thrown from a cliff. So there's me or you or whoever you want it to be throwing an object off a cliff like that. I want to know what is the maximum height and when will the object attain this height. So as it's being thrown, what is that maximum height? And when will it attain that? So think about it for a second, maybe pause the video. What am I actually asking you to look for? What are we being told to do to solve for? Well, the maximum height itself would be part of the vertex. If I'm thinking of the vertex as x, y, the maximum point, this time the y value is actually height. We've changed the y-axis to h. The secondary question is, when will it attain that height? Well, that would be your t value, the t of the vertex. And I asked this in class today. I said, okay, well, now you know you need to find the vertex. What strategies would you use? And the initial reaction was complete the square, which is excellent. It's a great way to go right into vertex form, but that doesn't look very fun to complete the square. I don't have a perfect square out front. Don't have a perfect square in the back. I'm going to have to divide by negative 4.9. That's a no thank you from me. I would use this guy, where I go straight to my axis of symmetry, and I would use negative b over 2a. Negative b over 2a is going to be this vertical line directly through the middle of my parabola. It's going to give me t, and then I'll have to plug that back in to find h. So I'm actually going to answer the second question first. I'm going to use these values. There's b. Negative b would be negative 55. And then 2 times a. This is where 4.9 turns back into 9.8, that negative 9.8 value that we saw. So this is what I'm going to type into my calculator here to find my axis of symmetry, or when it'll reach that height. So I've got 55 divided by negative 9.8. Oh, I think I missed one.
Attention MMW, can Amelie Wong please go to your bus? The bus is waiting. Amelie Wong, please go to your bus. The bus is ready to leave.
That's how you know your boy is still grinding at school, am I right? I'm sorry, but I'm not gonna redo the video from here. You can see my time in the top left corner too. But that's good. Amelie, make sure you get to your bus, you know what I mean? Don't want to miss that, making everybody wait for you. Anyway, here we go. There's my axis of symmetry, 5.612. I'm going to use 3 decimal places in my answer. 3 decimal places in my answer. Like that. But one thing that we talked about in class today is our friend, the answer button. The answer button is down here. It is above the negative symbol. It's written in blue, meaning I have to use the second symbol, and then I'm going to hit answer. And what that's going to do is when I plug this back into my equation, I don't have a rounded decimal. It's using this entire long decimal for me. I'm going to get a super accurate answer, and I don't have to retype in 5.6122 the whole thing every single time. So now I'm trying to find the actual height. I'm trying to find this orange height. So I'm going to use this time to do so. This time of 5.612 and onwards. And I'm just going to plug right back into this equation. I've got negative 4.9 times this decimal squared plus 55 times that decimal plus 63. And again, for me, I'm going to use that answer button. So I am accurate. I'm as accurate as possible. And B, so I have to type the whole thing in every single time. So here goes. I've got negative 4.9 times my previous answer squared plus 55 times, please use my previous answer, the A and S button, plus 63, and it's plopping in that 5.612 decimal. There is my height, the highest that this object will go, 217.337. And I don't think it gives us units. So there you have it. So the maximum, this is what I'm going to write, the maximum height, 217.337 feet or yards or whatever you got. Nice. Okay, I've got 2 more examples. If you want to, this would be a good opportunity to pause the video, work ahead and see if you get it right. Then you can fast forward me a little bit and rewind, of course, if you want to go through it a little slower or maybe you made a mistake or something. So this one, an object is launched directly upward. We do have a unit, 64 meters per second, from a platform 80 feet in the air. And I'm going to go ahead and fill in this equation, initial velocity there, initial height on the end. And I think it's really helpful to draw a diagram. So we've got, I don't know, maybe he's hitting golf balls off a really tall building. That'd be kind of fun as long as you're not aiming at other people. So we've got an object flying through the air with an initial velocity of 80, or initial height of 80 meters. The question here is, when does the object hit the ground? So if I'm thinking about my graph, the ground would be the x-intercepts. I could even draw a better graph here. There we go. That makes me feel better. I'm looking for the x-intercepts. Now, you may have seen this in my classroom. It's on the wall of awesome. It is extraneous busters. This is where we're going to get an answer that doesn't really make sense because the ball was launched from midair. So this part of the parabola doesn't really exist. It's negative time, which doesn't make sense. It was launched off the ground, so I'm not going to have that second x-intercept. When we find this with algebra, it'll be there within our answer, but we're going to call it extraneous. We're really only interested in that guy. Sure, it could bounce, but for our sake, it's only going to hit the ground one time, and then the problem's over. So if I'm looking for the x-intercepts, I think quadratic formula sounds good. I also think hitting the ground would be a height of 0. So here's my equation with a height of 0. And it's just to show you that quadratic formula is a really good option. You could factor. Again, factor's not going to be very fun with that negative 4.9 guy out front. Quadratic formula will always work, and it'll take care of your decimals for you. Again, we're going to use the answer key quite a bit. I'm going to start with my discriminant. My discriminant is that b squared minus 4 times a times c value. So I've got 64 squared minus 4 times negative 4.9 times 80. I'll go back to my calculator here. I'll even dual screen it so I can see both at the same time. And I've got 64, she ain't working. Hold on, there we go. 64 squared minus 4 times negative 4.9 times 80. That is my discriminant. Tells me that I'm going to get 2 solutions. One of them is going to be extraneous. Just makes my work in the quadratic formula a little bit easier. I've got x equals negative b plus or minus the square root of the discriminant, b squared minus 4ac, all over 2a. And we see negative 9.8 again. So here's where answer is going to be my friend again. I'm going to do the top of this quadratic formula, negative 64 plus the square root of my last answer. And then I'm going to hit divided by negative 9.8. That's 2a. There's my extraneous solution, meaning in the back here, we would have an x-intercept at a time value of negative 1 second, which doesn't really make sense. Another really helpful calculator tip is going and highlighting. So I'm using these arrows to highlight. I'm going to take the top of my quadratic formula again, and I'm going to change it to the minus version. And then again, divide by negative 2a. So we take my last answer and divide by 2a. And there's my other x-intercept at 14.21 seconds. So I've got this guy, and I've got this guy. And like I said, we're going to call this one extraneous. Extraneous, because it doesn't really make sense, and it would hit the ground after about 14 seconds. Okay, we're in the home stretch here, folks. One more problem here, and this one is a good one. This is your Justin Jefferson, where I want to catch it 5 feet off the ground. Now, you wouldn't catch it 5 meters off the ground. That's pretty tall. But I don't want the ball to hit the ground. I want it to be able to go through the upright. I want it to be able to go through this. So I am looking for, when does the object reach 5 meters? And it's important to note that this is h. So I want to know, when is h 5? Take a look at my equation here. I'm going to set h equal to 5. And I'm getting a little bit crunched by the algebra ninja guy there, but that's a good time to talk about. Now we can be a little bit tricky with what we want to do. We can be a ninja with how we kind of manipulate this problem. This isn't really one that we've talked about before, but it also kind of is. Because take a look at our daily problem. This is the same setup. As this would be like, okay, we'll figure out when it's 1 meter off the ground. Set your h equal to 1. And if I wanted to quadratic formula this, I would subtract 1 from each side. It's almost like Mr. Roach picks his daily problems on purpose. Crazy. So with this in mind, if I wanted to solve this, I wanted to solve for t, quadratic formula is a really nice way to do that. I just need to make sure my equation is set equal to 0. And I'm going to quadratic formula this guy instead. Kind of a side note, it would be like if you took your parabola and you moved it down 5, like subtracting 5 on the outside would take your parabola down 5. So you're like forcing an x value of 5, say this, or y value of 5 here. You're like forcing that to then be on the x-axis, which is kind of interesting. So you're forcing this down to move your whole graph down, and now we are kind of looking for our x-intercepts. Be like if your x-intercepts were 5, different, right? It'd be a value down 5. So same process as the last one. I'm going to do my discriminant first, which is x equals negative b plus or minus the square root of b squared minus 4 times a times c. I'll use my calculator for this. I've got 15 squared minus 4 times negative 4.9 times negative 3. 2 solutions here. We're actually going to have 2 normal solutions, no extraneous solutions this time, because if I look at my original graph, let me erase this scratch work here. Oh my gosh.
Wesley, Golio, your ride is here. Wesley, Golio, your ride is here. Thank you.
Can't make it up, you guys. Your teacher's out here on a Friday grinding and they're calling people down to the office. Okay, so if I'm looking at my original graph, here is my height of 5. That's my height of 5. I want to know when my purple graph is a height of 5. And this intersection here is actually going to happen in a positive t value. So before, when we were looking for our x-intercept, that x-intercept went to the negative land. It went into that second quadrant. But if I'm really looking for a height of 5, that's now in the first positive t quadrant. So I am going to have 2 normal solutions. And we'll have to consider both because it'll be at a height of 5 2 times, like right after it's thrown and right before it hits the ground. So the discriminant is positive, so I'm going to have 2 normal solutions. I'm going to go ahead and do my entire quadratic formula, x equals negative b plus or minus the square root of my discriminant over 2 times a. And again, I'll use my calculator to help me out with this. I've got negative 15, and I'm going to do plus first. Let's try that again. Negative 15 plus 166.2. There's the top of my fraction. Divided by negative 9.8. That's the bottom of my fraction there. So we've got one of our positive values. T is positive because it's going to be after it's thrown. In fact, it's going to be 0.215 seconds after it's thrown. And then calculator helpful here because I'm going back to copy this guy down. I'm going to hit subtract instead. It's the minus branch of our quadratic formula. And one more time, divide by negative 9.8. And you've got 2.846 seconds as your other 5 meter off the ground time. So there you go. That is applications of quadratics. To summarize, you've got to figure out, number 1, what am I looking for? And then number 2, how do I find it? So we talked about negative b over 2a for your vertex. We talked about quadratic formula. extraneous solutions. And then we also talked about, this is kind of interesting, is I can modify my equation, still set it equal to 0, and I'll find a specific height. So if you've made it this far in the video, I appreciate you dearly. I am around Monday morning. It would be Monday the 17th, 2025. I am around Monday morning for some help if you want to come in. I appreciate you watching this. The calculator was a little funky. We've got announcements in the middle of the video. It's a Friday afternoon. Mr. Roach is ready to peace out. I hope you have a great weekend. And of course, reach out with any questions. Peace.